Hello and welcome back to part 5 of the PIC12F683 video series. Today we're going to be looking at the on-chip SRAM. The basic element of any CMOS storage element is going to be an inverter loop. So we've got one inverter here, and then the output of that couples into a second inverter. So this forms a stable circuit. It will power up in an unknown state. One of the inverters will have a slightly lower VT than the other, or slightly higher drive strength, and it will end up creating a positive feedback loop. So which half ends up being high and which half is low is not deterministic, but it will stabilize very quickly after power up. Unfortunately, this circuit as drawn is pretty useless because we have no way to actually read or write. So this is typically done by adding another pair of transistors, with one NFET here, and then a second one coming out here. And we call that our word line, and then we have our bit line and our inverted bit line on the opposite side. And now we can actually read and write the memory. To read, we bring the word line to a high state. This then connects the inverter loop to the bit lines, and we can feed the positive bit line and the negative bit line into essentially a comparator and see which one is higher than the other. And that differential measurement will give us the value stored in the bit cell. To write, we also bring the word line high, but instead of reading the bit line values, we instead strongly drive one word line high and the other word line low with high enough drive current that it can overpower the inverter loop, essentially creating a momentary bus fight during the transition. And as soon as the inverter loop starts to get pushed past equilibrium, then the bus fight will end as the inverters begin to drive towards the new stable state. The loop will stabilize, it'll stop fighting the bit lines, and we end up having the new stable value. This bit cell architecture is typically referred to as 6T SRAM because it has 6 transistors. We have 2 in this inverter, 2 in this inverter, and then 1 here and 1 here. And additionally, it is also possible to have other SRAM bit cell architectures. You can do a 5T structure that has a single-ended read and write, which trades a slight area improvement for much slower access times. You can also do, for example, an 8T bit cell, which adds a second word line and a second set of bit lines and a second set of select transistors to make a dual port memory that can be read and written twice from different ports. And of course, for this bit cell to actually be useful, it's going to be built into a larger array, with the word line typically selecting, for example, which byte out of a larger array we're in, and then the bit lines are going to be the individual bits within the array.
So now let's turn our attention to the actual SRAM array on the PIC12F683. We are currently looking at the substrate with poly and metal removed, and the actual bit cell array is clearly evident. However, the logical structure of the array from the datasheet is 128 bytes, and the actual physical array is obviously not 128 by 8. Just glancing at this, you can see there's more than 8 cells wide. This is, of course, for practical reasons. It would be ludicrous to create an array that was the entire height of the chip and only a few microns wide. So to work around this, typically we use less rows than the logical memory depth and more columns, and then put muxes on the columns to select the actual bits we care about out of the entire physical memory row. And so in this case, we have a logical structure of 128 by 8, a physical structure of 32 by 32. And so if we have an 8-bit data bus and a 32-column physical structure, that means that we have a 4-to-1 column mux. And indeed, if we look at the top of the array, we can see that there are 8 of these readout circuits. And so this is going to contain the differential amplifiers for the bit lines, as well as a 4-to-1 mux. And then coming up out of the top here, we would expect to see the 8 data lines for reading and writing. And then down here is the word line circuitry, which will drive the word lines based on the row address that is input. And then up here is some additional decoding circuitry. And so we can expect that the row and column addresses are probably calculated from the overall input address in this area, and then maybe some additional buffering and conditioning. And we'll take a closer look at that later on. And before we get into the circuit analysis, I just want to show how technology has evolved over the years. So here is the SRAM from the PIC12F683. The bit cells are 5.73 microns wide, 8.23 high, which comes out to 47.15 square microns. And here in the inset, we have a STM32L431 SRAM. This is made on TSMC 90 nanometer, and at the same magnification, you can see just how many bits you can fit on one of these. The bit cell area on this process is about 1 square micron compared to 47 here. So you can fit 47 bits on a 90 nanometer memory on one of these. So now jumping up to the poly layer, we can see word lines running horizontally across the array. The bit lines are presumably vertical, and in fact, if we jump up to the metal 2 layer, we can see some of the bit line structures here. Again, we're not taking too deep of a dive yet, just trying to get ourselves oriented with the overall memory structure. And then we see some vertical lines here on metal 2 that are going down into the row circuitry. And then going up to metal 3, we can see there's obvious power and ground lines running across the entire length of the array, driving the bit cells. And then in between them are these skinnier wires, and these are actually parallel word lines. This is a very common technique you see in SRAMs a lot because poly has a fairly high resistance compared to metal. And so if we go down to, let's say, this view here on the poly layer, we can see that the physical bit line does span the entire length of the array, but trying to drive it from just one end, you're dealing with this very large resistance, and by the time you get here, actually trying to turn on this transistor may take quite a while with the parasitic capacitance being driven through this giant resistor. And so if we look more closely, we can see there's actually a contact every 8 bit cells that goes up through the entire metal stack, all the way up through metal 1, metal 2, and finally up to metal 3, and then ties onto this parallel word line, which is just there to provide a quick low resistance connection down to here. So rather than having huge voltage drop in the poly word line, we have a very low voltage drop here, and then the current is able to go down to the poly and drive it from all ends at once. So now we're going to switch from looking at separate images to looking at aligned tiles. I've hand stacked and aligned individual tiles in GIMP. This is nowhere near the full chip, just the portion of the SRAM that we care about. So now I'm going to turn on a couple of the layers that I've already traced. We've got the diffusion region, poly, contacts, and then metal 1, which if I turn, I believe, this one on, you can start to see the images here were not great. There's a little bit of unetched oxide, but there were enough bit cells that I was able to figure out all of the pieces that I couldn't necessarily see in one cell. The joys of repetitive patterns. Anyway, so thinking back to the schematic on the whiteboard, we can clearly see the coupled inverter loop right here. So we've got power connected up to the PFETs. We've got ground connected to the NFETs, and then we have one inverter here, and then a second inverter here, and the output of the left inverter couples directly to the input of the right one, and the output of the right one couples directly into the input of the left one. So here's our storage element, and these are the outputs of the bit cell, and so these then go through another NFET here, another NFET here. So looking at metal 2, we can see the bit lines running north-south, and then they do continue, if I turn this layer on, we can see they do continue up into the sense amplifier and column mux circuitry, but I had to stop somewhere or this video would be a week long. So we're just going to stop the analysis at the bit lines and then shift our focus over to where the word line comes from. So now we're up to about the metal 1 layer. There's some partially etched metal 2, but mostly metal 1. And we can see that there's this repetitive looking pattern here running all the way down the entire height of the memory array, which I don't have in all of the other images because it was all the same. But in this part, if we look closely, we'll see it's actually not quite the same. It's more obvious if I turn on metal 2 right here. And we can see that there's a couple of vias here, 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 and so on. And they're not in quite the exact same places each time. So, for example, if we look at this row here, we've got a via here, but not one here. Whereas here, there's one here and here. So this is clearly related to address decoding. So I'm going to turn on the tracings since some of those are a little bit hard to follow, especially the via 2 layer. And we're going to go back to this image because the contrast against the yellow color I used for the vias is a little bit better. And so it's pretty clear that we've got a similar but not identical pattern here. But every row has exactly 5 vias, which is interesting because we have 32 rows. That is consistent with these somehow being related to address bits. But of course, how do we know which row is which? We're not just going to be feeding in the raw address bus to here and then having a hardwired is equal to 0, is equal to 1, is equal to 2 circuit, because that would take up too much space. And of course, these vias are in different places, so there must be something fancy going on in the decoding here. So we can see the first couple of lines here seem to be paired, where there's exactly 1 via in each group of 2 of these vertical lines. So we've got left, 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 right. Right, left, right, right. That sound familiar? And so it looks like we essentially have a binary counter with each bit encoded by 2 lines, and exactly 1 of these is going to be brought high at a time. And so to verify our hypothesis, we can go up to the row address decoding circuitry here, and I've already traced all of the lower layers, and we can see that this rightmost line connects here, and the next one connects here, and we've got a pair of NFETs and a pair of PFETs. And if we trace out some of the connections, so this is power, and then there's some ground wires that I didn't fully trace out to metal 2, but we know that this is going to be grounded in some way. So we've got something coming in on metal 3 from the right side of the array, and if we jump up to the metal 3 image here, we can see this is going all the way out of the SRAM array, actually going over here. So we're looking at this region here, and we can see there's a bunch of lines coming out of this decode circuitry that are going all the way off somewhere into this dense routing on metal 2 in the core of the device. And so following them in this way, we can see that this first line here is going in to what looks like a CMOS inverter. So we've got power here, ground here, and then our input. So that means that this metal strip here is the output. And if we then follow that onto metal 2, we can see that this left line here is inverted of this. But then also, that same metal line continues down to a second inverter here, and this inverter then has the output on this metal 1 line here, which couples up to this metal 2 line, and goes here. And so we can confirm that these 2 lines are in fact being driven as essentially a differential pair. One is always the complement of the other, and they're also essentially a differential copy of this signal here. So if we have a signal coming in from the outside of the SRAM, and it's being split into a differential signal, and the very first thing that we see is we are using the inverted version of it in the first row and the non-inverted version in the second row. That means we're looking at the low row address pin. So we're just going to somewhat arbitrarily call that a 0. And if we repeat this process up here, we can see that we've got address line A1 right up here. And so I've labeled a few of the signals now to make it a little bit easier to follow what's going on. So now if we follow these signals out from the address decoders, we can see that they jump down onto metal 1 for a short time and then onto poly, and they go into something here. And what we're probably looking at here is essentially a 5-input AND. And so we have one of these is indicating that the corresponding address bit is in the correct state for this row to be activated. So if this is logical row 0, that means that we have address 0 is 0, address 1 is 0, address 2 is 0, address 3 is 0, address 4 is 0, and so on. So coming from here, it comes out from this AND circuit and then goes into this giant inverter right here, which is presumably to increase fan out. This small circuit here probably doesn't have a whole lot of drive strength, and then continues on out to the word line right here, which I've helpfully labeled, and goes on to the actual bitcell array. Now, noting that there is an inverter on the output, that does mean that what we've got here is actually going to be a NAND 5, not an AND 5, since we need to have a second inversion for the word line to be in the high state when the row is selected. And we can also see that there's this additional signal on metal 2 that is getting mixed in there somehow. This is probably a clock or a read enable or something to gate the word line, so that regardless of what's on the address bus, we don't actually want to energize the word line unless we're trying to access the bit cell. And so this is presumably the gate for that. So at this point, you may be thinking we're done. We fully understand the addressing. And I thought that at first too. But then I looked a little bit closer and I started to wonder, because if we count these vertical lines here on metal 2, there's 12 of them. And if these were in fact just differential versions of the address, we only have a 5-bit row address. There's only 32 rows in the array. And so why is there a 6th pair? And if we zoom down here, we can see it's not just like dummy fill or anything. It is actually connected. And it's connected in a somewhat confusing pattern. So typically, if we're counting in binary, we would expect to see alternating with a period of 1 row, with a period of 2 rows, with a period of 4 rows, and so on. But actually tracing out the pattern of vias, we can see that it's a little bit more complicated. It looks like it's almost following this pattern at first. So if we look at the first 3 address bits, we can see exactly the pattern that we expected from what we had reverse engineered during the address decoding logic. And so we've got the first pair is alternating every row, then alternating every 2 rows, then alternating every 4 rows. And so this is in fact just differentially coded addresses. But then we get here and we see something a little bit different. In the high half, we are in fact alternating just like we expect. But then this one goes high and then this one goes low, and it stays that way all the way down. We would expect these two to trade places in the last 8 rows, and they don't. And then here, we see an alternating pattern like we expect, but then they're both low, and this other line comes in. And then this one goes high for just 4 bits, but this is toggling here, so it doesn't make a whole lot of sense at first. So I was initially wondering if this was some kind of weird, like, modified gray coding or something, and there might be some way that the decoder would use less power or something if they used a strange addressing scheme, and it didn't make a whole lot of sense. And then somebody on Mastodon pointed me to a section of the datasheet that I'd actually completely forgotten. I used to write code for this chip all the time, but I was mostly doing it in C, and so I didn't actually have to care about the physical memory address map all that much and exactly where my variables were laid. That was something the compiler mostly took care of for me. And so I had completely forgotten that although this device does have 128 bytes of RAM, it's not actually a contiguous 128 bytes. It's actually a 96-byte region mapped at address 20 in bank 0, and then another 32-byte region mapped at OXAO in bank 1. I had it stuck in the back of my head that, hey, yeah, this is an 8-bit microcontroller. It's got, a banked addressing scheme because we want to be able to address more than 256 bytes of memory plus control registers. But I had assumed that since there was only 128 bytes of RAM, it was going to occupy a contiguous 128-byte region of address space. And as it turns out, that is not in fact the case. So I went back to my spreadsheet and I plotted out this address map and assumed that the top of the array was the first address in the logical memory map. So in this case, we're at OX20 of bank 0. And then going over here again, remembering that we do have 4-byte rows because of the column mux, and so OXBC is going to be the highest addressed word line in bank 1. And so if we plot this out and we look at what the actual address bits of these addresses are, so looking at the bank ID followed by here, it's a nearly perfect match. And so now everything starts to fall into place. We've got the bank ID bit here. That matches perfectly with the bank ID here. And everything up here is essentially just this converted to differential, but also ANDed with bank address equals 0 so that we don't alias with the stuff in bank 1. And then jumping back here, now we can see some of this other. So if you recall, we only actually traced out these first couple of inverters. And so now we know what all this other logic is doing. That's essentially the single-ended to differential conversion for all the other address bits, as well as the ANDing with the bank ID equals 0. And then presumably some of this is responsible for driving the column address as well. Again, we've got 4 bits of bit line going into a 4-to-1 mux, and so there's going to need to be some select bits being generated by some of this logic as well. But we're going to leave that, as they say, as an exercise to the reader because this video is already getting too long, and I'm going to need to move on to the flash and the EEPROM before we can wrap up.
And that's it for part 5. If you've been following along as these have been released, I do have slightly disappointing news for you. This is as far as I've actually gone to date. I am actively working on reversing the EEPROM, but it's probably going to be another week or 2 before I've got enough analysis done to actually get part 6 up. So stay tuned and I will post it when it's done.